Okay, well, sounds good. Okay, so welcome to lecture 16, and I want to do more on travel time curves, specifically how that applied to the earthquake stuff. We ended Tuesday's lecture beginning to learn a little bit about P waves and S waves. Does anyone need a reminder of what a P wave or an S wave is? Okay, yes, you do. Okay, fantastic. Then this is good. There's all these little videos, but we're going to go here and listen to this one right here. Let's see if this is going to work. So here is one of these little videos. This idea of what seismic waves are. So this is some fancy geophysicist sort of fellow. Dr. Butler. He's a geophysicist, so he obviously knows what he's talking about, or he should. So let's just take a look here as a little review of what these ideas are about P waves and S waves.
Let's talk about different kinds of seismic waves and their paths that they travel from an earthquake to a distant seismic station. One kind of waves, the body waves, travel through the interior of the Earth. These are of two varieties. There's P waves, or sometimes referred to as pressure waves. They're the fastest. There's S waves, or shear waves, which are slower than the P waves, but they're faster than the surface waves, which go around the perimeter of the Earth. The rate path, the path that these P waves and S waves will travel from an earthquake up here to a seismic station over here would be through the interior of the Earth, through Earth's mantle. And in general, the P and S wave velocities increase with depth into the mantle, so they're going faster and faster as they go deeper into the Earth, and then they slow down as they approach the station from below. In addition to these body waves, we have the surface waves, which travel around the perimeter of the Earth. They oscillate the outer few tens of kilometers of the Earth. There are two varieties of these, radiant waves and love waves, named for the people who discovered them. So their path of travel would be around the perimeter of the Earth, shown by this set of arrows here. Because they travel in the materials near the surface, which have lower seismic velocities, slower velocities, they will arrive substantially after the body waves have already arrived at a distant seismic station.
Okay, so the point there is you've got a few different types of seismic waves. A seismic wave, you could think of it as a sound wave as applied to rock. And because rock is solid, not only does it support compressive waves, basically pushing, it can also support these shearing sort of motions, a different kind of wave. And the important point that he said was these P waves travel faster than the S waves. The density of the rock is one of the things that sets how fast these waves are going to go. Once you know a bit of modeling about how the waves, the seismic energy propagates to the Earth, you can use it to infer information about earthquakes and let those earthquakes infer information about the Earth. And the tool is something called a travel time. How many seconds or minutes or hours it takes for a wave, a seismic wave, seismic energy to propagate from an earthquake to a seismograph, somewhere where a little needle is going to jump up and down and detect it. So that idea about the travel graph is the other idea I want to just summarize. If I can figure out, I want to go back. Why can't I go back? Where's my back button? Did it open a new window? Oh, it's just being fancy. Okay, here we go. Travel time curve. So what's the idea of a travel time curve?
So here you go, distance from the earthquake, and here's P waves, they're the fastest, right? That's the first thing that's going to get to you. And then here's S waves. So it takes longer for the S waves to get there for any given distance. And here's surface waves. Notice, when you're here, within a few hundred kilometers of an earthquake, the S waves and the surface waves are basically not distinguishable from one another, but they are distinguishable from the P waves. And this difference in time is sort of linear with the distance that you are from an earthquake. So for a regional earthquake, it's actually pretty easy to do this exercise. So if you observe, you got a seismogram, you observe the P wave arrival, and just as an example here, let's say it arrives at 4 minutes and 15 seconds. The S wave arrives at 8 minutes, then you get this 3 minutes and 45 seconds. And if you look at this, 3 minutes and 45 seconds only fits one place on here. And so that defines for you where the earthquake was, how far away from that one station.
Okay, so the idea here is this is how you go about figuring out where an earthquake occurred. If you knew these curves, these S-wave and P-wave travel curves, and you see in your seismogram a pulse comes through and then a few minutes later another pulse comes through, what that tells you is how far away that earthquake was in terms of distance away. You do that for a few different seismic stations. You can infer where the earthquake was and how strong it is and such. What I want to do is do some simulation, do some modeling with the ray equations, that is treating the wave like an object which is traveling at a velocity given by the density of the rock, and come up with these travel curves. Figure out why they've got this shape, why the red one and the blue one curve the way they do. That's sort of what I want to look at in this lab. So let me just do this, and do this, and do this, and do this. Okay, so what we need is some model of what the Earth looks like in terms of its density. We're going to use density and the velocity of sound through that, the velocity of the seismic waves, some model of what the Earth is. Now, you will know that to a good approximation, we live on a round Earth, right? So we can assume that as you go from the outside of the Earth towards the center, the structure of the Earth is basically the same. This is an example of what's called a 1D Earth model. Yes, there are continents, so if you come at the Earth from the North Pole or the middle of the Pacific or the middle of Antarctica, you're going to have a slightly different structure, but by and large, the structure of the Earth, thinking its crust and its mantle and its core, is basically independent of direction. You can think about the structure of the interior of the Earth as having one dimension, a radial dimension, and it doesn't matter what direction you're going all the way through. These models are called reference Earth models. That is the idea that we're going to take the density or rise of the speed of sound inside the Earth and plot it just as a function of how deep we're going to go. So there's several one of these models. These things are inferred and figured out by looking at earthquake data and working backwards to come up with what they are. But I can go and I can search the web and find such a model. So there's a model called the IASP 91 model, a paper from 1991, that explains how fast a P wave and an S wave will travel as a function of the radius. So here's the model. There you go. That's the model. All the model is a bunch of discrete points telling you how deep you are going. So into the Earth, 19 kilometers, 20 kilometers, 34 kilometers, 120 kilometers, 360 kilometers, all the way down to the center. How fast a P wave's traveling? 5.8, 5.8, 8, 8, 9, 9 in sort of kilometers per second as you go into the Earth. And then there's the speed of the secondary waves. And then if you want to, there's the density going all the way through. And the point is, if you scan along this list, the density of rock up near the surface is 2-3 kilograms per liter squared, basically, right? So it's thousands of kilograms per meter cubed. But at the center of the Earth, you've got some fairly dense rock, right? A nice dense solid core, getting up to about 13,000 kilograms per meter cubed, something like that. If we want to visualize this model, because the model is just a bunch of numbers, basically a table, what I can do is I can put these into arrays and make some plots. So I'll import my modules as we've been doing. I'll load up these arrays. I'll recognize that the radius of the Earth is probably a pretty important constant somewhere in there. It's about 6,300 kilometers. So you either can talk about the depth from the surface into the Earth or the radius of the Earth from its center out. Either one is just fine here. If I take those models, which are just a bunch of discrete points, I can interpolate them so that I can figure out what the speed of a P wave or the speed of an S wave is at any depth all the way through. This is something you can do with interpolation. We talked about this briefly. This is not best fit. This is basically connecting the dots of the line to come up with 3 functions. Now, VP, VS, and rho are actually functions that we can plot. So if I try and make that plot by creating the subplots and then plotting as a function of radius, this velocity P and the velocity S, you can see that this is the Earth model. It's a 1D Earth model in the sense that it's only a function of radius. And as you go from the surface of the Earth, so this is up here. Remember, the radius of the Earth is around 6,300 kilometers. As you go deeper into the rock, it gets more dense, the velocities increase, and this is what we're seeing. It increases, it increases, it increases. Something happens at about 2,500 kilometers down. There's this sharp change. So those of you who have done like Earth 101, what happens at about 2,500 kilometers down? The outer core, right? There's a fundamental change in the nature of it, right? So you go from this solid mantle, right, to what happens at that outer core? It's not solid anymore. It's liquid. Okay, so it's liquid, right? Liquids have seismic energy propagate differently through them. So take a look at what's happening to the speed. First thing, the speed of these P waves drops down from about 14 down to 8. What does the speed of an S wave do when it hits this outer core, this outer liquid core? What speed does it drop down to? 0. Why does it drop down to 0? Exactly. Okay, and that's the important idea, right? The shear waves don't travel through liquid. They don't travel at all. They reflect off that core. That one of the reasons we know that there is a core there is because we can model S waves and P waves to the Earth and go, hey, something interesting is happening at about a radius of 3,400 kilometers from the center. So that's the idea of a 1D model. Now, if we're going to talk about a 1D model, we want to still think about the Earth as sort of having a center core and an outside. So I think this information is better displayed on a polar plot, as in radius r and an angle theta representing where you are as a cross section all the way through. So I think a better way of displaying this is with some sort of polar plot. And Matplotlib understands the idea of different projections. And so if you look up in the gallery, there's a bunch of projections, and one of them is a polar projection. This means that it plots things not in X and Y, but in R and theta. And what the code does basically is it figures out a whole bunch of different R's and thetas. For every one of those R's and thetas, it calculates the density, and then it plots that with a bunch of contours all the way through. How it does this is not too important, but here's the kind of picture we get. So here is my slice or cross-section of the Earth. So this is a density field. You can see that the outer density, it's getting denser and denser. The color bar is increasing as you go in. You get to this sharp transition as you go to the outer core. And then there's this other kind of transition in here. I assume that's the inner core. Is that what the fancy technical name for it is? Okay. And of course, that's solid inside there. So you're seeing those sort of bands. That's the structure of the Earth. What I want to do is I want to model, just like you saw in that little lecture, of a wave, a seismic wave propagating through the Earth. Now, everything's symmetrical. It does not matter where we put the earthquake. So just for the sake of argument, let's put the earthquake as being right up here, okay? We're going to say that that's the starting point of the earthquake, and we're going to model these waves propagating into the Earth and looking at the curves that they make as they go into the Earth. That's what we're going to try and figure out. The equations of motion, as we went over on Tuesday, are the ray tracing equations, basically saying that the velocity is given only by where you are. The velocity is a function of x and y. It travels at a speed given by that velocity in some angle. And I'm going to use the symbol phi to represent the direction it's going, which is different than the theta of where you are in x and y in polar coordinates. And as you're moving, because the velocity is always changing, because the density is always changing, we use Snell's law to figure out how the angle is going to change all the way through. Whether or not you write these equations in terms of x and y, or in terms of polar coordinates, r and theta, is totally up to you. It's just a change of coordinate system. As soon as you know x and y, you automatically know the r and the theta, the polar coordinates, or vice versa. I have to have two different symbols for angle. This theta here refers to where in the earth I happen to be. The phi refers to what direction I'm headed, to make it clear. The mapping is r is equal to the magnitude of x squared plus y squared, or theta is equal to the arctan. And x equals r cos theta, y equals r sine theta, just in the sort of normal way. So when I think about this kind of transformation, what I'm imagining is I've got this circle, and I'm basically putting the origin right at the center. The x-axis is left to right. The y-axis is up and down. And we're talking about an angle we're making with respect to here, so I can plot any dot on this polar plane. That's how I'm doing the transformation. Okay, if we want to solve these equations, we need to take the right-hand side of the system of equations and define something that's going to solve them. We've talked about this a couple times. I'm going to shorten it up by defining a sine and a cos. I need to evaluate the derivatives of the velocity. I need to evaluate di v di x and di v di y. I don't know those explicitly, but I have a function for v as a function of x and y, so I can estimate those derivatives numerically. I'm doing that using a center difference scheme. And then I just need a right-hand side of the equation, the equations of motion. This is just the derivatives of all the variables in my system. In my system, I have a derivative with respect to x with respect to time, derivative of y with respect to time, and a derivative of the angle with respect to time. I take those three derivatives and I give them back. So what this function does is it takes in the state, whatever the current, where the ray is, what its x coordinate is, its y coordinate, and the current direction it's headed, and calculates what the rate of change of that state is. This is the purpose of that function. It's the right-hand side. Once you define a right-hand side of a function and include some initial conditions, you can solve for the motion. So here we go. Let's define some initial conditions. Let's suppose that our initial location for this earthquake is right at the top of the picture. x0 equals 0, y0 is equal to the radius of the Earth. So I'm going to send my earthquake starting from right there. I could send it from anywhere, but I'm going to start from that location. Pretend there was an earthquake at the North Pole, but you can always turn the Earth. It could be wherever you want. I need to have an initial direction it's going. So I'm going to have this thing pointing down at some angle all the way through, at some angle. I have to come up with an initial state, and then I'm going to simulate how this ray progresses. I'm going to run my model for 800 seconds. I don't know how long it's going to take to go all the way through. I know it's several tens of minutes. So I'm going to use a tool, a solver, that comes in the SymPy called ODE integrator. You can use any integrator you want. I'm just going to use this built-in one. You pass into it the right-hand side, the initial state, and all the times you want to solve for. You can actually pass in additional arguments as well, because of course the speed of this thing depends upon the velocity model. That is how the velocity depends upon where you are on the planet Earth. So what I'm doing is I'm passing in as an additional argument, this is what args does, a particular velocity model, namely the velocity of a P wave. If I was to change this to Vs, I'd be looking at the ray path for an S wave. I solve it, I iterate through, I come up with some data, and let's make a plot. So here's what you get when you solve this model. And of course, okay, here we go. So this is an X and Y space. Yes? Why did I use a comma after the? Okay. Python thing. Python has this idea of lists. It also has the idea of a tuple, which is sort of like, you don't want you to do a function, you say f of a comma b. Okay, the of a comma b is a tuple, a pair, an ordered pair of things. And you can go a comma b comma c. What happens if you want to, so you can have an a comma b, an a comma b comma c. You could have nothing. But what if you wanted to have a rounded bracket with only one thing in it? To distinguish between that and the parentheses, they put a comma. So that's not, it's not a double or a triple, it's a one tuple. It's a Ordered pair, it's an ordered set of one thing. Well, now you still have one thing. That's a list of one thing. If you get rid of the comma, then you don't have a list of anything. So it's defining its list of one thing. It's a idiosyncrasy. Okay, fair enough. Good question. So here is the path. Remember, we're starting off at the top of our planet, near the surface, at a radius of the Earth away from the center, and it's propagating at an angle to the vertical into the Earth, and it comes out at the radius again. Now, to understand what's going on in this plot, it's helpful not to only plot x versus y, but to plot the variables all versus time, because there's really a time series going on. X, y are changing with it. So what I can do is I can calculate maybe the radius of this as a function of time, and then plot x versus t, y versus t, and the radius versus t to really understand what the trace of the ray is. So here we go. As a function of time, how many hundreds of seconds? You can see that the y coordinate starts off high, the radius of the Earth, and drops down to about halfway through. The x coordinate starts off at 0, the center of the planet, and moves towards the edge. And the radius shrinks from near from the surface of the Earth down to about 1,000 kilometers, 1,300 kilometers down, and then pops back up. Notice that after about 600 seconds, these numbers all become constants. The radius becomes the surface of the Earth, the x becomes the surface of the Earth, the y becomes whatever it happens to be. That's the energy popping out and hitting the end of the Earth. The energy can't go anywhere because the velocity right at the edge where there's no more rock, I've set the velocity equal to 0. So basically these waves propagate until they hit the edge of the planet, the surface of the planet, at which point the velocity is just set to be explicitly equal to 0. So it sort of stops. What this means is I can model these things now. So this particular ray, which started at an angle of 45 degrees to the vertical, it will reach the surface again at about 600 seconds after it launches. Well, 600 seconds, 60 seconds to the minute, so about 10 minutes it takes this wave to propagate through the Earth. Now, rather than visualizing this in x and y, we can also think about this in terms of polar coordinates. We can figure out what the x and y would be in not just r, but r and theta. We've already seen it here for the polar coordinates. Let's write a function that does the job of solving the system of equations. It's going to take some arguments. It's going to take as an argument what angle to the vertical you're going to send this thing in. It's going to take as an argument how long you want to run it, how often in time you want to feed back the discretization in time, and what velocity model. And it wraps up the whole application. Sets the initial conditions, defines a time array, integrates it, and then also calculates what r and theta is all the way through. So it does all of the business work of running our model. I'm going to call compute ray running the simulation. It's really the thing that does all of the work calculating how one of these rays does its thing. Now, if you look at it, square root you might have seen before. Arctan is a little bit weird. Where does arctan come from? Arctan, by definition, mathematically, is a function which returns a number between minus, well, I got to make sure this right here, minus pi over 2 and plus pi over 2. It's only got a range, which is the whole pi. Arctan 2 lets the angle be anything in a 360-degree circle. Arctan by itself has a range of plus 90 to minus 90. If you want the arctan to be angles that are going to be obtuse, arctan 2 is a variation on it. See documentation if you want to know. Okay, let me show you how this works. So I am going to compute a ray. So this function, we can now just use this as a model. We can run it. Given some angle, and this is relative to 9 degrees, so it's been shifted down. This is an offset from where it is. It runs the model. It takes a few seconds to run, and that's the first few rows of the data. So after the first second, the third second, the first second, second second, third second, fourth second, you can see that it is going into the Earth, so y is decreasing, and it is beginning to bend ever so slightly at an angle x as it moves. This number right here is changing. It's just changing in a very, like, several significant figures to the right. You don't even see it moving. If I take that data, the r data and the theta data, I can project that on top of our polar map, and we can see this ray propagating through the Earth. Okay, so this is similar to what we saw in the lecture. These curves, which start somewhere and they bend through and they pop up somewhere else. We can say that this ray has traveled a distance given by this arc length, right? So from here to here is 45 degrees. From here to here is about 50 degrees. So we can say it traveled about 50 some odd degrees along the surface of the Earth. And if you know the radius of the Earth, you can turn that into an actual distance. But this is the kind of model of a single ray that's been launched at an angle of 45 degrees from the vertical into the Earth. Another way of thinking about this line is to plot this thing as a time series, right? So there's the polar plot representation of the model results. We could also talk about a time series result. So this is just taking the plot of the data and plotting r and theta as a function of time. And we get these two graphs. This is the polar coordinates, radius and angle, as a function of time. So these are two ways of visualizing the path of this ray. You either can think about it as an xy coordinates plotted in polar coordinates, or you can think of it as a time series of r and theta. In both cases, you're seeing that it hits the edge, that is the surface of the planet, and pops out at a certain dimension. It travels for about 600 seconds or so. One of the things we want to calculate is how long it takes these waves to propagate. So we need some method of taking this data and extracting out this number right here. We need a routine that, given some model output, you do a simulation, we want to know what this number is. We don't want to have to make the plot and then read it off manually, though you could. We want to write a piece of code that can figure out how many seconds it took for that ray to go through the planet. That's called travel time. Okay, we can read it off and you can go, okay, it's about 560, 570, somewhere in that ballpark. You can sort of see the little bend. To travel this dimension from 90 degrees to 35 degrees, from 90 degrees down to 35 degrees. So rather than reading off the graph, let's write a function that figures this out. So here is my version of this function. There's lots of ways of doing it. We're just going to do a simple loop. We're just going to loop the data. We know we start off at the surface. So let's start at the very next point, point 1, and ask, is the radius beyond or equal to the surface of the Earth? If it is, stop. If it isn't, go to the next data point. We're basically just looking down the table going, is the radius bigger than the surface of the Earth? Is the radius bigger than the surface of the Earth? At some point, it will be, and that point will be whatever I is. I will stop moving, and I will be at that location where it is, and we can return back the distance and the time taken. However, if it goes to all the data, and that ray hasn't yet popped out, it hasn't gone all the way through, let's just return not a number, because it hasn't finished yet. Okay, so if I run it for this data, you can have a function which says, okay, this thing took 585 seconds and it traveled a distance of 56 degrees along the surface. So these are tools that we can use to come up with our travel time curve. Okay, so we figured out how to solve it. So there's a function called compute ray. We've looked at how to plot the data, as in what it looks like in cross-section. We have a tool to plot its time series, and we have a tool to figure out how long it takes a wave that traveled at an initial angle of 45 degrees into the Earth. What we want to do now is run multiple models. We want to run this model for lots of different initial angles. You can set a ray into the Earth and have it go in at some angle to the vertical. Each one of those angles is going to produce a different kind of ray, and that ray is going to have a different travel time. That travel time is going to be related to the distance that it goes. Let's put these pieces together and create a travel time curve. Now, this takes a bit of time to run because you are solving a more complicated model. I'm only going to solve it for 4 different initial angles. Now, these are offset angles. So they're angles in the sense of I'm going straight down, and then I'm adding a little bit of angle in terms of radians. So I'm straight down plus 0.1 radians, or straight down plus 0.3 radians, or straight down plus 0.5 radians. I want to run my model multiple times. So this list here is a list of all of the model runs, all the simulations I want to run. And I'm going to loop through this, but I'm going to use this function right here from a library called TQDM, which gives me a nice progress bar. And what is good about this is I run this model. You have to import the library first, of course. You can see that it's giving us some indication about how long it's going to take to run. It already tells us there's 4 parts to this. It's going to have to run 4 times. And as soon as it runs the first time, it measures how many seconds it takes to run, and then says, okay, we've done it once. You just need to wait 3 times that before it's over. It took 18 seconds to run for the first simulation. I've got 3 more simulations, 56 seconds to wait, taking about 18 seconds per simulation. The nice thing about these progress bars is it tells you whether or not you should just be patient, or if this thing says come back in 2 days, come back in 2 days, right? This is good because otherwise you don't know if your program is just broken or not, right? You know how sometimes you get this little gray dot and you're like, did it break? No, it's not breaking. It's just working. It's computing. It's doing its stuff. And when it's all done, it goes green. What I've done, and on average, it took 13 seconds for every iteration. That's what IT stands for. What I've done is I've stored those results inside of a data structure called a dictionary. Results is a dictionary that allows me to look up the results of the model simulation associated with each one of these initial angles. I'm basically saving the results so I then can analyze them afterwards. I wouldn't want to have to recompute this data. It takes 13, 14 seconds. I don't want to have to recompute it every time I want to plot it. I want to do the simulation once and then plot it several times afterwards. This is a very common thing in computer simulations. We run models. These models run for hours, days, weeks, months. They generate data. Think hundreds of terabytes. You put them on computers, and then you look at it afterwards. You don't want to have to regenerate this data all the way through. Very common model for running these things. Okay, so once you have the data stored in this data structure, rather than looping through this list, I can loop through the actual values of the dictionary, the contents of it, and just pull out all of those data sets and show you all of the data in one go. So what I've done is I've sent in 4 different rays. My first ray is straight down, and then I've added an angle of 0.1 radians. My second ray, I've straight down, and I've added an angle of 0.3 radians, 0.4, 0.7, 0.9 radians all the way through. You can see that this first one is very close to a 0.9 radians, it's close to a pi over 4. That's very similar to what we had the first time. There's the second one, there's the third one, there's the fourth one, or vice versa. Now, there's a bit of a problem here. You can see from this graph that these 2 red lines didn't make it all the way through. Now, is that because they got to the center of the Earth and they just stopped? No, it's because we didn't run the simulation long enough, okay? So if I go and plot the time series curve, so again, what I'm doing is I'm looping through all the elements in this dictionary. I'm picking off what the value is of that initial angle, and then what the contents is. This is an idiom you could use. And I'm getting a plot for each one of those runs for each curve. I have a legend. So the blue one is the 0.1 angle. The orange one is the 0.3 angle. The green one is the 0.5 angle. You can see that the red one and the blue one, the red one got to the surface after just above 600 seconds. The green one just made it to the surface in 800 seconds. But the blue one and the orange one haven't quite got there yet, right? You needed to run this simulation for longer to be able to make it work. Well, I don't necessarily need to waste the computer time to rerun these first two simulations. They worked fine. There's no point in running that simulation again, but I can rerun these two simulations to extend them further on. And you can play with this, or you can just infer it from the graph. Basically, you got to go to about 1,300 seconds for those simulations. So what I can do is I can rerun that model, recompute the simulation for the same starting angle, but pass in a longer time period. So rather than running the model for only 800 seconds, let's run it for 1,300 seconds. Now, it's still going to take a moment to work. It'll probably take about 20 seconds now per iteration, but it should be faster than running all four of those models again. I didn't put in a little progress bar because for 2 it didn't make sense. But if you had 20, maybe you'll want to put a progress bar in there to figure out how long you need to wait. The important part here is I'm not rerunning all my simulations. I'm just rerunning a few of the simulations. And anytime now, anytime, it is working. I'm sure it's working. It's just thinking. Once this completes, we can now make a plot of the time series again to confirm that you've actually got all of those rays getting outside of the Earth. They've run the simulation long enough for them to pop out. Of course, we're also working this computer because my guess is you all did the same thing. Yeah, okay. Fair enough. Fair enough. Come on, computer. You can do it. Don't break. Don't break. Okay, we're going to let that finish. And then when that's finished, I want to take a look at a plot of what it all looks like. Good point to pause for questions. Is this idea of a set of tools for analyzing a model making sense? I've got a tool that runs the model. That's compute ray. I've got a tool that lets me visualize the rays. I've got a tool that lets me see how long it took to run, the path of them. There we go. So you can see that the blue one and the orange one, it took about 1,180 seconds to get to the end. I could have run this model for only 1,200 seconds. But I did not need to rerun these or run them anymore. I just replaced their results. We can figure out the angle. In terms of a cross-section, here we go. So if you let the model run long enough, you see that that ray actually popped out on the other side. An earthquake located here, it would travel through the outer core. There's a bit of a change in direction when it goes to that interface, and it pops out over here. Okay, these are the kind of pictures we were seeing in the plot before. And in fact, if you go and you look at Wikipedia on these kind of plots, you'll get pictures that look like this. Okay, so this is a textbook thing of the propagation waves of P waves. And you can see that it's got the same characteristic pattern where they bend and they come around here. Or if the wave is shallow enough, it comes around here. So you can imagine making this plot by playing around and adding more lines and more curves to your data. My point is, here is something which looks relatively complicated, but we've just calculated those numbers by doing a ray tracing model all the way through. Now, there's something that the model identifies. It says, actually, you're never going to get a signal here. This is called the P wave shadow zone. It's because of the core of the Earth. As the energy propagates out, it either bends and pops out on this side, or it goes through the core and pops out on this side. There'll be no signal from here to here. Indeed, from our simulations, we can see that that shadow zone is there as well. So what we've done is we've got a model now showing us different rays and how far they travel in the sense of degrees. We also know how long it takes for them to travel through it. So what I can do is I can make a little table. Okay? I can say for every one of these initial angles, there's a certain time in seconds that corresponded to a certain distance in angle. And that's what a travel time curve is. Now, I could take that and I could build it into a data frame, just basically rearranging this thing. So rather than just printing them all off, I'm going to compute a travel time data frame. Okay. So this is just a pretty, rather than leaving it like print statements, this code is making up a list going through every one of my results, figuring out how long it took in terms of travel time, sticking the angle in there in the table, and printing them all out. Now, Python's a fairly compact language. So if this idea of starting with a list, iterating through every element in the dictionary, building up the row, adding it, and then turning them to a data frame, if that idea makes sense, then you may be comfortable just doing this one. It's exactly the same thing. This magic code is the same as this. Data frames actually accept iterators. This idea of a loop is an iterator. And so what you can do is you actually can use something called an iterator. This is a dictionary iterator to give you back, or a list iterator, to give you back a set of dictionaries all the way through. I don't care which one you use. If you're like, no, that doesn't make any sense, this makes a little more sense, use that. If you're happy with the short form, that's good too. The point is they both give you a data frame with the same numbers. And once I've got the data frame, once I've got a column for times and a column for distances, I'm able to make a plot. I'll plot of travel time, and rather than seconds, let's turn this to minutes, versus distance. So this is a plot of distance in terms of degrees, distance around the edge of the Earth, given how much time it travels. If you want more dots on this page, you need to run more simulations. So if I run a simulation with an initial angle of 0.6 radians from the vertical, and depending on how many of you hit the button at the same point, there we go. I could rebuild that data frame and plot it again. And now I have one new dot right here. You can imagine making lots of dots, dot, 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 dot. And what you'd be doing is reconstructing this travel time curve. Does that make sense? Okay. That's the background and the theory. What I want to do, and I want to sort of do this collectively, iteratively, I don't know how we want to do it. I want to look at a particular earthquake. So here was an earthquake that happened a couple years ago. They happen all the time, but here's one. It happened in 2016 in Italy. Okay, here we go. So, and we could do this for any earthquake, but I just happen to have the slide borrowed from that same site all the way through. So there was a magnitude 6.2 earthquake that occurred in the region of Italy at a depth of about 6 to 10 kilometers. Now, it was fairly serious. 120 people were killed. I remember hearing about this one on the news. And it destroyed a town in Italy. It was detected to occur at about that spot right there on the Italian peninsula all the way through. When seismograph machines, when seismic instruments in different places in the Earth looked at the data, here is what they got as their spectrogram or their seismogram. So it's very similar to the plot we were seeing in the video. There is a seismic instrument located in the town of Bend, Oregon. It's in Bend, Oregon, because that's where this group IRIS is based. If you notice, Dr. Butler teaches from there. That's where he's got a seismograph. This is the record of the seismograph as received by a seismic instrument in Bend, Oregon. And you can see that there's a certain number of minutes between the P wave and the S wave, right? That allows you to figure out where this earthquake occurred, in the sense of, if you know that the distance in time was from here to here, you could read off this graph by putting this transit curve at the one location where the S curve and P curve are a distance of 12 minutes and 31 seconds apart, and figure out that the earthquake had to have occurred a distance of 84.4 degrees away. Degrees in the sense of travel around the arc of the Earth and go 84 degrees away, or about 9,300 kilometers. That's where this earthquake must have occurred. These curves are the travel time curves. Now, this display just gives you in text. It says, hey, because of this curve that geophysicists know how to calculate, we can figure this out. And here's what I want to do. I want you to use the model that we've developed, this compute ray term, to try and estimate how long do you think, or would you model, a P wave would take to travel a distance of 84.4 degrees. Okay, this is the forward problem, not the inverse problem. But the idea is I want you to send out rays representing P waves into the center of the Earth, construct a travel time curve, basically this black line, and try and figure out the one that took 12 minutes and 31 seconds to propagate, or rather, given something which is 84.4 degrees away, start with this point and figure out where this would end up on the map. Figure out this curve and check whether or not you also get 12 minutes and 31 seconds, and then do the same thing for the S wave and figure out whether or not you are able to confirm that an S wave propagating a distance of 84.4 degrees takes 22 minutes and 55 seconds to propagate. Okay? Rather than depending upon this site and these curves that have just been drawn, I want to see if we can use this model I've come up with, this seismic ray modeler, to come up with these numbers. So the way that that's going to work is we're going to have to fill in this curve so that this relationship, you see the 84.4 right there? There's no dots right there. What I'd really like is to have an estimate of 84.4 and try and figure out what time that is. Basically, go from 84.4 to the right here and estimate what time that is. And the way we're going to do that is we're going to fill the graph in. We're going to put a few more dots in this space so that you've got a better estimate of the travel time. And then if we really want to be fancy, we can interpolate the whole thing. Maybe we won't be that fancy, but we want to sort of figure out what points would go right here and come up with our estimate of how many minutes it will take. So here's the lab. I want to, using this one-dimensional reference Earth model, use the functions compute ray, plot time series, and travel time to estimate what it is. How long does it take a P wave to travel a distance of 84.4 degrees? And then we can compare that to the observed value, or the one reported in the literature, of 12 minutes and 31 seconds. And then we're going to do it for S waves all the way through. Now, I said I want to sort of do this collectively together. We're all going to do it. I'm going to let you sort of play on it. I'll help you. We can come back and do it as a group. I'm not sure the best way of doing it. For the lab itself, if you switch over to the lab, what I've done is I've taken the libraries we need, repeated the question, and then just taken the code from this lecture. The reference Earth model, the interpolation functions, the ray tracing equations, the solvers, the time series, and the example. That's all the code. And here is the complete example of what we were doing. So here is how to run a series of simulations. So I'm only running the one for 0.5 and 0.7. Okay. You always could add in more. You'll need to add in more. You'll need to choose which particular angles make sense to have the rays end up where you want them. Come on, it took 18 seconds. 18 seconds. Ah, 24 seconds. Computer's slower because more people are using it. And if you all just went through and ran everything, then it's going to bog down, but it's fine. Once we run it, we don't need to run it again. Just got to wait another 24 seconds. See, I'm going to skip this block. There we go. I don't need to run this cell. This would just create more rays. I don't know what values to put in here. We have to sort of figure that out. All right, these are the two rays. I want something that travels a distance of 84.4 degrees. If I look at the time series, okay, what you can see is these two things traveled a distance from 90 degrees down to between here and here. In terms of just tables, right? Initial angle of 0.5 traveled a distance of 92 degrees. That's too far. Initial angle of 0.7 traveled a distance of 66 degrees. That's too short. I need to fill in this curve so that I know if I take a line from here, 84.4, where's it going to end up? There's a bit of a curve here. We need to figure out the dots between these. My guess is running these two values. Right? They're bad angles because those guys are going to send off going through this direction. We need more angles that are in this range. Try and run a few additional simulations to fill in the graph so that you've got some points which are going to let you do a lookup from 84.4 to try and infer what the travel time is. Once you've got more points in this data, you can do a NP polyval sort of fit to it. It should look, I don't know what shape it's going to look like, but it's got some curve to it. You could fit a curve and then evaluate it at 84.5 and figure out what the actual time would be in terms of minutes. And then do the same thing, but do it with an S wave all the way through. Does that make sense in terms of what the goal is? You're trying to come up with your own value of 12 minutes and 31 seconds. It won't be 12 minutes and 31 seconds. It'll be 12 minutes and something. It better be close to 12 minutes though, or this totally doesn't work. So that's the idea. So I'll wander around, talk in groups. I am all good if all of our code looks the same after a little bit of time, but that's what I want to try to achieve. Yes? Okay. The first line. This one. Oh, just restart your kernel. Well, we'll figure it out. Okay, sounds good. I said I'll walk around, take a look at what people are doing, and we'll finish it off.